We're going to go over the FRQ from class the other day. I just wanted to kind of put this out there in case anybody had any questions about exactly how to approach an FRQ or of this kind. First things first is we are given a set of data. This is my x coordinates. We've got my y coordinates for my linear regression model. This was really nice. In fact, in this example, they've given me pretty much everything that I need in order to be able to analyze this regression output. In some examples, you may have to make the graph yourself where you're only given this. In some instances, you're only given this, so we aren't even able to make the graph. But what's important here is that I recognize what I see. Number one, with the scatter plot, I can tell that this is a very linear graph. It looks like it's very strongly correlated, and it's a positive association. I can confirm the linearity by looking at the residual plot. Here, you see all the dots all over the place. There's really no pattern, and that's one of the ways we can judge if it's linear or not. If there's no pattern at all in the residual plot, you've got a linear model. Here, we don't even have a problem with the standard deviation or the equal variances assumption. It looks like it's all pretty good. We don't have that kind of funnel shape that kind of grows on one end. If I look down at the bottom down here, we're given a lot of values to kind of consider. It's nice that they've given us the line of best fit right here, so we know the slope, we know the y-intercept. We can also see those two values show up in the values at the bottom. My slope's always going to be the value right here, and my y-intercept will always be the top one in that first column. Slope's always the second one. Other things that is important, this is the standard deviation of the residuals. This is going to be the r-squared value, so 96.7%. If I take the square root of that and look at the slope sign, I can tell you what r value would be. In this example, what we have is lots of extra stuff, right? R squared adjusted, ignore that. All of these things we will get to in due time, but for now, we just want to focus on this part and these two values. Sometimes you're given this value up top where you can see the line of best fit. A lot of times you're not. Okay, let's go on and look at the questions. In this question, part A, zoom out a little bit, it's asking, is the linear model appropriate for these data? Clearly explain your method. In this example, as we saw earlier, yes, the residual plot shows no pattern, so a linear model is appropriate. You can go back and look at it. You can see the residual plot. We talked about it a minute ago. It's just a big scatter of dots. And that's really what I'm looking for. If there was a pattern, that would be a really bad thing. It would suggest that the linear model would not be appropriate. A different model would. Part B, this is the one that if you're going to have an issue with this, this is probably the one that gave most people the hardest time. This example, or this part says, suppose fuel consumption cost is $25 a unit. Given value, give a single point estimate for how much it's going to cost in fuel per mile for each additional rail car. Well, we were told in the problem that 2.15 was the slope, right? And my values was for each additional rail car, we would expect to spend, we would actually use 2.15 units of fuel on average. That's the definition of slope. You look back at our scripts for this chapter, and slope is one of those. We also know that for each, if I'm using this much fuel per car, for each additional car that I'm adding, and this is the amount of money that I have to spend on each unit of fuel, then I would simply multiply these two values together to tell me how much it's going to cost for each car's fuel amount, right? And so it would be $53.75. So the math is here. The explanation would be we would expect to spend $53.75 on average for each additional rail car. I say it's on average here because this is not an exact value. This is just an estimation, right? This is just an estimation, so that I don't need to kind of at the end kind of tell you that it's going to be exactly $53.75. Just an estimate. All right. Part C. Here again, we have another interpretation, another script that we've learned to memorize. If you haven't done that, definitely take some time to do that. It says 96.7% of the variation in the fuel consumption can be explained by the variation in the number of rail cars. I've really just taken r squared and put it in context, right? Here's your percentage, this is your y variable, and this is your x variable, right? The number of rail cars. I don't have a whole lot of explanation on that. Look that script up. If you go back to the week overview for this week, I put the scripts in there right for you so you can kind of just copy and paste them, get used to seeing that. I'm definitely going to ask you to do that on the quiz today if you haven't already done that, and I'm going to ask you to do that on the test. It's coming. Okay, the last part, D, it's asking us to predict for 65. If you go back and look at the original data set, it gives us data all the way up to 50. Right? So up to 50 rail cars, we can talk about a model that predicts it with the slope and the y-intercept. Is it reasonable for me to extend this all the way up to 65 rail cars? And the answer is no. It's not a reasonable endeavor, because if we have to do that, we're not sure that that's going to have the same result. At some point in time, I know that you're going to have to add an additional engine to pull a train that large. I don't know the number, but we do know that we don't have data outside of 50. This is considered extrapolation, right? Extrapolation is never something that we trust. It's because we don't have any evidence to suggest that the pattern that we're dealing with right now continues on forever, right? So anytime you're extrapolating, you're always not really going to trust the results there. It's one of those things where you can do it, and sometimes it works, sometimes that's great, sometimes it's not. So in a general rule, we don't really tend to trust our extrapolation methods. Okay, so that's the reason there. It's just, we can do it, which is not something we'd trust. And that's it. That's pretty much all that answer is. And take a minute and go through that. The FRQ that I've given you to do today to turn in actually is a little bit less involved than this one is. So hopefully this kind of gives you the idea of what is expected and what you can do to turn that other one in on time. If you have any questions, please let me know. Send me a message and I'll get back to you as soon as I can.